In last lesson's minute physics video, you were given a little bit of a teaser in reference to the fact that it was mentioned that a current will produce its own magnetic field. And this is believed to be the reasoning behind why some substance become magnetic, because the electrons that are moving around the moving around the nucleus are basically carrying their own little current and therefore producing tiny little magnetic fields. We're going to explore that on a larger scale here, and I just want to provide you a little background before we begin. In around 1819, I believe it was, there was a fellow by the name of Hans Frederick Oersted. Probably would have been a good thing to have done before I started here, but anyway, this Danish by the name of Oersted discovered in 1819, totally by accident. He was actually doing a lecture to somebody. He was a professor in a university or college, and he was doing a lecture, and he noticed that when there was a current running through the wires that he was using, that a nearby compass would move. I only imagine what it'd be like for myself teaching a lesson. Something weird happens, and all of a sudden I'd made a discovery that basically going to change physics, and this really did. Up until this point, electricity and magnetism showed some similarities: the positive and negative, north and south, attract and repel, but they also showed some differences. The monopoles that you can get in electricity, the solely plus or the solely negative, versus the dipoles that you get in magnetism. Always a north always having to have a south. So they were seen to be similar, but not in no real way related. And when Oersted noticed the moving compass when he ran current through a conductor, that kind of changed things. So when he ran current through a conductor, a nearby compass moved. The interesting thing about this is that it appears as though Oersted was actually not the first person to discover this, although he's the one who's giving credit for it. There was an Italian physicist that a few years before this, actually 17 years before this, made essentially the same discovery, but instead of publishing it in any kind of reputable science journal, he published it in a newspaper. And nobody really made much notice of it. Again, getting back to the idea, if I were to find something that appeared to disobey the laws of physics as I understand it, I'm just going to assume that I did something wrong. And I'm also not a professor and one of the leading people in my field in this particular topic, so it wouldn't surprise me to think that I had something wrong. Well, this Italian guy didn't think he had something wrong, and just nobody would believe him, so it kind of died. And then 17 years later, Oersted came around and discovered this, and it had some credibility, so we moved on. And that's what gets us to what is now called the principles of electromagnetism. I'll often call this Oersted's principle, because really he was the one who came up with it. And the kind of nuts and bolts version of Oersted's principle is, or the principle of electromagnetism, is that when a current flows in a conductor, a magnetic field is created in the region around that conductor. and it's that magnetic field that caused the movement in the compass. And so this is a very vague statement. It's basically just saying, yeah, this does happen. It's not saying anything quantitative about it. It's not saying really all that much qualitatively about it either. It's a starting point. Because for hundreds of years before this, electricity and magnetism were considered two totally different things, similar but different. And this is the first time that things appeared to be not what they seemed. Now, this actually did have a huge impact on physics, because things that weren't seemingly related appeared to be related. And the other thing that we looked at is this kind of action at a distance, that running electrical current in one place could affect a compass in another place. We'd seen that with gravity, we'd seen that with electrical forces, we'd seen it with gravitational, with magnetic forces, but never combining the two. At this point, even the idea of energy was not really well understood. So this was yet another thing that kind of led people to believe that there was some mysterious substance or mysterious quantity called energy that was being moved around. And there was actually a lot of competition and a lot of infighting amongst physicists around this time, and a little bit after, kind of the old school versus the new school. Unfortunately for us, the new school won out, and this was basically the beginning of actually of Einstein's thought process when coming up with his theory of relativity. So it seems a little far-fetched right now, but it is closely related. From Ørsted came Faraday, who we're going to talk about a little bit later, and from Faraday it kind of gave his ideas to other people, and Einstein picked up on those, and he ran with it, and then the whole world of modern physics starts. So this is kind of this whole electromagnetism stuff is a transition between old or classical physics with with Newton and people like that, into more modern physics with people like Einstein and Hawking and Niels Bohr. So let's take a look at some more details of this whole idea of electromagnetism. Well, the first thing we're going to do is look at a series of rules. Actually, the majority of what we're going to do is look at a series of rules involving what we call a right-hand rule, because we know that when a current runs through a wire, that's going to create a magnetic field. So the first right-hand rule, if you look for, is for a straight wire. So let's say here's our wire, okay, and our wire has a current going up through it in that direction. Okay, so that's which way the current is going. According to the first right-hand rule, what you need to do is you're going to point your thumb in the direction of the current. Now, not surprisingly, because it's called the right-hand rule, you need to do this with your right hand. Remember that current is the flow of positive charge. That is extremely important here. Otherwise, you're going to get this totally backwards. Current is the flow of positive charge. The positive charges are moving up. Now, we know the positive charges aren't moving, but as we discussed before, you can think of it as the positive charges being the empty spaces that the electrons leave when they jump from one atom to another. So the positive charges are moving up this wire, and so if I take my thumb and I point up the wire, and I'm actually doing this right now, I know you can't see me, but you try it anyway. Look at your screen, point your thumb in the direction that the wire is going. Now here's the important part. Your fingers will curl in the direction of the magnetic field produced by the current. So, point your thumb straight up, kind of like you're hitchhiking, and your fingers will when you kind of partially bend your fingers, like you're going to make a fist with your thumb pointing straight up, but don't totally bend your fingers. So start with your hand perfectly straight. So your fingers are pointing straight out in front of you. Your thumb is pointing up in the direction of the coil. And now just curl your fingers slightly. And if you now kind of rotate your wrist, you'll find your fingers will lead in a circle. And I'll draw this in a different color. One of the issues that we have here is this is all going to be three-dimensional problems here. For those of you who think well in 3 dimensions, this is going to be a breeze for you. For those who have a little bit difficulty in 3 dimensions, you might have to spend some time on it. But the difficult part is drawing 3 dimensions on a 2-dimensional surface, and I'll show you some tricks for that later. But I'll do the best I can with this. So in this case, your thumb is pointing straight up, and your fingers on the left side of the wire. You notice your fingers are basically going to be coming out of the board, in front or out of your screen. In front, your fingers will be pointing towards the right, so it'll kind of look like this, and then they'll go behind, and then come back out here. Excuse me, let me try that one more time. So if we draw a direction, it's coming this way in front, it's going that way and back, and you're going to get this circular type of loop. You might actually, if you want to try this, take a pen or something like that, hold it straight up in front of you, grab the pen with your thumb moving up the pen, and look at it and look at which way your fingers are curling. They're curling around. If you look straight down on the pen, they would look like they're curling counterclockwise, and that's the direction of the magnetic field. So right-hand rule basically it implies that you're going to create a circular field around the wire that kind of goes in a circle. Now let's look at an easier way to draw this. And so let's say that we're going to look downwards, like I said before, looking downwards on the wire. So here's what your wire would look like. I'm going to draw it on the right side over here. There's what your wire would look like. So we have a little trick, and it kind of borrows a little bit from the idea of archery. When something, if an arrow is coming straight towards you, and you think of the tip of the arrow being like a little point. So if something is coming towards you, and we draw it like a little dot. So that represents a vector or a direction coming out of the board, out of your screen. If it was going in, then we would have drawn it. So this represents current coming out of the board. So now let's try this. We'll talk about what happens when it's coming in a second. So you can now put your thumb in a direction coming out of the board or out of your screen, out of your paper. So your thumb is pointing right towards you. So you kind of see that little dot from the tip of your thumb. And follow the directions that your fingers will curl. In your right hand again, your fingers will curl in a counterclockwise direction around the wire. So that black wire in there, the black line is the wire. The dot represents the current coming out towards you, and the blue line represents the magnetic field around the wire in a counterclockwise direction. If the current is moving into the board, then we would draw it like an X, and we think of the X kind of like the feathers of an arrow. Now, I know that there's usually only 3 feathers at the back of an arrow, but that's fine. It's just an analogy. So this would represent current going into the board. And so if we point our thumb into the board and we look which way, or into your screen, and we look at which way your fingers will curl, they curl in the opposite direction So they curl going clockwise around the wire here. So you'll see that the field changes direction. And it kind of makes sense when you think about it. If we were to look at our example at the top here, if we look at this from the top, from a top view, it looks like our magnetic field is moving counterclockwise. If we look from a bottom view, it would look like our magnetic field is moving clockwise. And you can try it out. Again, put your thumb in the direction of your pen, overlapping your pen. You see which direction your fingers curl. Look at it from the top, and your fingers are pointing in a counterclockwise direction. Look at it from the bottom, and your fingers will be curling in a clockwise direction. So both of those seem to make sense. So that's right-hand rule number one. It's the starting point for all electromagnetism. So our next step would therefore be to look at right-hand rule number 2. And right-hand rule number 2 is for something that we call a solenoid. What a solenoid is a coil. It's a current-carrying coil. So a coil with current in it. And these solenoids can be made to be wrapped fairly loosely. They can be made to be wrapped really, really tightly as well. And I'll show you how we draw these. Again, it's a three-dimensional problem, so drawing these can sometimes be a little bit difficult. So what I like to do is draw a material like a tube, think of it like a toilet paper roll type of material inside the tube, and I draw my wires around there. So I'm going to draw my wires in black, and so I'm going to have a wire come up front, and then it goes down and back, and then it's going to come up the front, down and back, and it's going to keep doing that. And it's going to come out here, and let's attach this to some sort of a power supply, and bingo. So first thing to do here is to identify the direction of the current. Now remember, I'm going to remind you every chance I get here, current is the flow of positive charge. So it flows from positive, there, towards the negative. So it's going to go this way, and it's going to go up there. It's going to go up in the back, and it's going to come around the top, and it's going to go down in the front, and it's going to go towards the back, and it's going to go up in the back, and it's going to go down in the front, up in the back, down in the front, up in the back, down in the front, and then back towards the negative over there. So the way that's the first thing you need to do. So the way that right-hand rule for solenoids works is that you take your fingers and curl it in the direction of the current. So it's opposite to what you did in the last one. Fingers curl in direction of current. So in this case, I would be taking my right-hand rule, and I would be basically like I'm grabbing this coil in one hand, and my fingers have to go in the same direction of the current. So my fingers will point down in front. So you would see me basically cupping my hand, so my fingers are pointing down in the front of this diagram. They would be going up in the back and down in the front. And I can show you, if you're having trouble visualizing this, obviously I'll show you what this looks like in class, but try to figure it out based on the descriptions that I'm giving you. I guess if I could try, this could turn out really, really badly. But let's look at there, my fingers. Okay, and my hand kind of curls a little bit like that. Where does my thumb go? My thumb's out here somewhere. Trying to make this actually look a little bit like, wow. Yeah, well, something like that. This is why I'm not in art. Anyway, I think the fingers started off okay, actually, and your coil would kind of fit right in here, between where my palm is, right there, and where my finger is. That's my fingers pointing down. Hope that helps. I'm starting to realize that this might not be the right method to teach this particular topic, but we'll see how it goes. So your fingers curl in the direction of the current, and what you'll notice is that your thumb should be, if you're doing this properly, your thumb should be pointing to the right. So your thumb points in the direction of the magnetic field inside the solenoid. So I'm going to use my green lines here. So the field inside the solenoid is pointing that way because my thumb is pointing to the right. When I grab the solenoid in that way, my thumb is pointing to the right. So there's my field inside. But as we mentioned in the last lesson, magnetic field lines don't just start and end. They have to loop back around. So this field actually comes out like that and comes back around. And the field lines will continue. This would do something like that. And so the field lines would continue, go all the way around, and come back. Same thing is happening over here. Let me erase my beautiful artwork over here. This field would come around and loop back. This field would come out and loop back. And so the field would look like that. So one of the things that I want to point out, and let's see if I can do this here. Let me create a rectangle. One here. Okay. Take that little rectangle, put it down there, fill it up with. Oh, I don't know. Let's go with an aqua type of color today. There we go. Now, if I take this and put it back over top of there, what do those fields, maybe I can draw a few more field lines out here as well. Out like that. Okay, coming in like this. Now, what does that look like? You've seen this kind of field. You saw it today in class. You probably see this in other places. It kind of looks like a bar magnet. And now if this was a bar magnet, then this side here of the bar magnet is the field lines are pointing away from it. So at the field lines, remember, point in the direction that the north pole of a magnet would point to. So it would point away from the north and towards the south. So what we've essentially have here is we've created a bar magnet. But it's a bar magnet created by electricity. So in other words, it's an electromagnet. And the right side of this particular electromagnet behaves like the north end of a bar magnet, and the left side behaves like the south end of a bar magnet. So another way to look at the direction your thumb points is that you could say that your thumb points towards the north end of the electromagnet. So I can now remove that box and bingo, we have our electromagnet. The advantages that we have of an electromagnet over say a bar magnet is, well, one obvious one is that you can turn the electromagnet off. I can't turn a bar magnet off, but I can easily turn an electromagnet off. So if you want your magnetic field to stop, let's say you're working in a junkyard and you're using magnets to lift large pieces of metal, I can turn the magnet on. it magnetizes the metal, I can lift it, and when I want to drop it, I just turn the magnet off and it drops. The other thing is that the magnetic field is extremely strong inside. So if you look at where the lines are and the inside, they're really, really tight together. So it's a very, very strong field. On the outside, the field is actually fairly weak. So I don't need to have a huge, huge electric or magnetic field in order to create, in order for it to be really strong where I want it to be strong. I can have a weak field around the electromagnet and still have a strong field inside the electromagnet, depending on how we put it together. Let's look at another example and see if you're getting this. I'm going to create an electromagnet. Let's put my little toilet paper roll. Now this toilet paper roll that I'm talking about, it just to give you the general shape, because my artwork certainly doesn't. But it could be filled with anything. And in fact, we're going to talk about how we would fill in this coil. In fact, you don't need anything there whatsoever. All you really need is wire. It's hard to create a coil of wire without wrapping it around something, but you can do it, and it would work. So let's say I'm going to take my wire and I'm going to wrap it around like this. So a typical question on a test might be something like, draw the magnetic field around this electromagnet. And in order to do that, now you could try drawing the magnetic field and probably get the right shape and maybe get it going in the right direction. But I'm going to want to see all of the steps that go along with this, because there's a whole bunch of little things. And you could consistently make mistakes that will totally cancel each other out. And so the first thing I'd want to see is for you to identify the direction of the current. So positive to negative. So it's going around that way, to the left and back, and then it comes out front, and it goes to the right in the front. And if you keep following that, it's always to the right in the front, and always to the left in the back, and back towards the negative end of the battery. So, knowing that, I have to take my fingers and wrap them around. So in front of the coil, my fingers will point to the right. So my thumb, if you're doing this correctly, your thumb should be pointing upwards. So if your thumb is pointing upwards, that means that this right here is our north side, and that is the south side of our electromagnet. And I can create the magnetic field away from the north towards the south. Now notice that the field points towards the north on the inside. That's okay. It's away from the north on the outside and towards the south on the outside. It always has to be a continuous field. So it might look a little bit like that. Didn't have much room on the left side there, so that's what our field line would look like. Now, when I said you could make mistakes that would cancel each other out, so one of the things you could do is you could have the current going the wrong way, and that's totally going to flip everything over. But if you then accidentally think that your thumb is going to point in the direction of the south and not the north, then those two mistakes will completely cancel each other out. Now you've made two mistakes on this problem, but you get the exact right answer. And so that's why I'm going to want to see all of the steps that you have going into this. So drawing the direction of your current, drawing the north and south poles, drawing your fields, and then putting the arrows on the direction of your field. So the next thing I want to take a look at is factors that affect the strength of this electromagnet. So think to yourself, if I want to make a stronger electromagnet, what are some of the things that I can do? And some of these things will be obvious and some will be surprising. The first thing, maybe the most obvious thing, is the current. As the current goes up, the strength goes up. It's not necessarily directly proportional, although in this case it does tend to be. We're not going to get into anything mathematical. There are some questions in your textbook dealing with the proportionality and strength. Don't worry about those questions. Just skip by, move on to something else. I just want you to know that these things can have an effect. And as you get more current, it means you have more flow of charge. It means you have more of those little tiny magnets creating a magnetic field, and you get more a larger magnetic field. So a stronger electromagnet. The second thing, as you can imagine, is the number of loops, but it's not just the number of loops, it's how packed those loops are. So it's number of turns, and we'll call it turns or loops, per unit of length. So in other words, how tightly packed the wires are. So I can have a lot of turns, but my electromagnet might be 5 kilometers long, and so they're spaced apart. That's not going to help. You need to pack those turns in, so you need to overlap them one on top of each other, which means because of that, there is an indirect relationship with the width of with the thickness, I guess, of the electromagnet, or the width, the radius of the electromagnet, because the lower the radius is, the less wire that you need in order to create the same density of loops. So if it's a really big, let's say like a huge culvert, so like a big drain, and you wrap your wire around that drain, you need a lot of wire to make just one loop. And because you have a lot of wire, it means you have a little bit of resistance in that wire. It means your current's going to go down. So when the loop is small, when it has a small radius, you don't need as much wire to make each particular loop, which means you can pack the loops in there. And if you don't have a lot of wire, you won't have a lot of resistance, and therefore the current will be high. So those two things together mean that there is some implication for the thickness, although directly it's the thickness or radius of the solenoid has no direct effect. The thickness of the solenoid does affect both the current and the number of turns, and that's why there is an indirect effect of the radius of the solenoid. The third thing is the material in the core. Each material has a certain amount of ability to allow magnetic fields to propagate, to move, to be able to move through. And the materials that have the larger amounts will obviously be able to create larger magnetic fields from the solenoid. So putting in a piece of iron, a core made out of iron, will make the magnetic field stronger around the entire magnet. Not just inside the magnet, but outside the magnet as well. Putting in a piece of wood, which doesn't have a large ability to allow magnetic fields to move around, well, that's not going to increase the strength of your electromagnet. There are some things that are actually create a lower magnetic field than air, and many things that create a larger magnetic field than air. So let's look at some practical examples. So the first one that you might have noticed is fire doors. We've had a few fire drills in the last little bit, and every time there's a fire drill, the doors in the hallways close, and that's done on purpose because so the electromagnets that are attached to the doors they usually have electricity running through them. Or I should say, instead of saying electricity, I should say, they usually have current through them. To keep the doors open. Okay, so we have our little electromagnet in here, and then we have our door, and on our door we have a little magnetic portion over here, and that they will attract each other and keep the door open. So when the fire alarm goes off, and the current shuts down, current shuts down, and the electromagnet basically turns off. And if the electromagnet turns off, then the door has nothing keeping it open, and it goes back to the shut position. We do this because we want to limit the amount of oxygen getting to the fire, and it slows the spread of the fire. And it's better not to have somebody go around and manually close all the doors. So this is an easy way to do it. All the doors will close at the same time. So that's a real easy and efficient use of electromagnets. Another one that's maybe a little bit more complicated is an electric bell. And you see them all over the place. And we, if it wasn't illegal, we might take apart our fire bell up above the door. But actually, I do have another one that I can show you in class to show you how it works. So let's take a look at the example on the right here. So this is a kind of a typical bell. You think of the bell probably as the gong. It's the part that makes the noise, but you need the whole thing. So let's take a look at the circuit. We've got a little push button switch. It can be any kind of switch that you want right over there. You've got a source of power, whether it be a battery or an AC or DC source, DC. You have the current, so the battery, the current's going to come out through here, and you've got a couple of little electromagnets. It basically creates a horseshoe magnet type of thing. So the current's moving this way, which creates the north end where it's labeled, and then the current moves that way in the opposite way, which creates a south end over here. You get a horseshoe magnet. Now you've got this little armature. I'll just call it the arm. So the arm is made out of a magnetic material. So notice that that arm, it actually is made to be able to pivot from here. So it can pivot right from there. And this part here is not attached. Okay, so it's just a contact point. And here we've got a little spring. And so what happens is that when the current is on and the magnetism is being created in the coil, it's going to attract this arm. So what's going to happen if the arm gets attracted? Then this thing is going to go. The hammer is going to hit the gong and create a noise. Ding. There you go. Ding. But what happens is this little point, this contact point, actually comes off. But when it does that, if you lose contact in your circuit, now you no longer have any current. Bye-bye current. And so now that you have no current, you have no electromagnet, which means that this arm is no longer attached, no longer attracted. So it was attracted, but now it's no longer attracted. So it goes back to its original position due to the spring. I'm not sure if that spring is exactly in the right spot there, but there's a spring that's going to pull it back. But as soon as it pulls it back, it reestablishes contact, which reestablishes current, which pulls the arm back, and bing, another strike to the gong, which disconnects the circuit, which brings the hammer back to its original position, which reconnects the circuit, which makes it strike the gong again, and just keeps doing this over and over and over again, and that's the sound that you hear as a bell. So there are other examples in your textbook. They talk about relays, and there's tons and tons and tons of different examples. Maybe in class we can talk about MRIs. I know some, at least one person is doing their project on MRIs. We can talk a little bit about that, and we'll go from there. Lots of little diagrams and things in your textbook. And once again, as I may have mentioned in class, if you do these questions and you understand it, this is going to be really easy. If you don't do the questions and just think, yeah, I got it, you could really, really mess yourself up. I see a lot of people who do very, very well in this unit, but I also see a lot of people who just crash and burn because they're trying to figure it out for the first time. And there's going to be some stuff that we do later on that's really similar to what we just did, but opposite. And so you need to know when to use which diagrams and which rules. So what we still have left to do, right-hand rule number 3, the motor principle, save that for the next lesson, as well as the idea of induction, creating electricity from magnetism instead of creating magnetism from electricity. We'll get into that next week.